Hey everybody, thanks for tuning in to Altium Academy. I am Zach Peterson, I am your host and I'm a technical consultant for Altium, and today we're going to talk about something that's really fun and a bit more on the advanced side in terms of PCB layout, and that is a quick intro into what are BGAs. Now if you're a new designer, the idea of a BGA may seem a little overly complex, but it's actually a really important type of component because it's one of those things that is used to make sure that we can mount components that have a lot of functionality in a single package. There are a lot of really powerful components that get mounted as BGA components, and so it's really important to know how to work with them in your PCB layout. Let's get into it. So a BGA is generally, not always, but generally a square-shaped component, could be rectangular, that has an array of balls that are arranged in this regular pattern. And so I'm not going to draw it all the way out. You can kind of see how this goes, but we have this regular pattern of balls arranged all over the component. And this type of component, and the acronym BGA, is a ball grid array. So when we say balls on a BGA component, we're referring to solder balls that are on the bottom of the component. So the bottom side of the component has a bunch of solder on it, and when you're going into assembly, basically just place it onto the footprint, heat it up, solder melts, adheres to the board, and you're done. I'm oversimplifying a little bit, but that's kind of the idea behind these components. Now, these balls that are on a BGA component, essentially arranged like this generally, but if you actually look at a real footprint, or if you look at a pin diagram in the data sheet, sometimes you'll see one of these missing. So maybe this guy is missing, or maybe one of these other ones is missing. So just keep that in mind. But like I said, generally it's going to be all the way across, all the way down the component. These components have to have a specific footprint, obviously, and you need to put that footprint into your PCB layout, but you also need to determine how you're actually going to route traces into these components. Now, the reason I bring that up is because how you actually work with these components, how you create a footprint for them, or what is in the footprint, and how they're going to be implemented in a stack up depends on a couple of factors. So it depends on here the size of the pad that you need to support this ball on the bottom of the component, but it also depends on this value here, and this value is really critical. This value is called the pitch, or P. So if you ever hear someone say coarse pitch or fine pitch BGA, they're talking about this distance between these balls on this BGA. So coarse pitch just means large pitch. We're typically talking about like 1 millimeter down to maybe about 5 millimeters. For fine pitch, generally less than 0.5 millimeters. Kind of two realms of BGA usage. Generally, as the pitch gets smaller, then obviously the ball size has to get smaller. As the ball size gets smaller, what has to happen to the pads? Well, the pads also have to get smaller. And so what we're going to do now is we're going to look at kind of the anatomy of these pads and how you actually get traces into this BGA. So I'm going to draw this out and we'll be right back. Okay, so I've gone ahead and drawn out a 6x6 BGA, pretty small BGA. Generally, if you're working with a BGA, I mean, there's really no like lower or upper limit to the number of pins or the number of balls that can be on a BGA. So like I've worked with BGAs that have hundreds of these balls on them. And I'll actually show an example here coming up. And then there are some smaller like common microcontrollers that actually come in a BGA footprint. So STM32 comes in a footprint like this. So wide variety of components that use this type of package. The next thing we want to look at is how do we construct the pads, and then how do we route into this? So two really important points. First, let's look at how do we construct the pads. You're going to have a pad that has to accept this particular ball on it, and you're going to create this array of pads, and that's what's going to be in your footprint. The specific pad size, you don't have to go through and like figure this out with an equation or anything. If you actually look in your data sheets, they will have a recommended land pattern that will basically tell you the size of the pads and then how the spacing, obviously. So that's what's in the footprint. Inside of a BGA footprint, what you'll actually see is not just the pad. There's a solder mask opening around the pad, okay? So the solder mask opening is really important. Generally, the pad will, come off just to the edge of the ball, just a little bit, and then the solder mask opening will come open around that. So This is a solder mask defined pad. So what that means is that there's a little bit of solder mask opening here, and that defines this pad size. And so what happens on the actual pad during assembly is when you're soldering the component onto the pad, the ball melts a little bit, and then it sits in this reservoir that's defined by the solder mask. So the solder mask creates kind of like a dam that holds that ball, that holds all that molten solder in place. And so that's what you'll see on a BGA footprint once these things start to get really close together and you have really high ball count. So the next piece is, how do we route into this? So this is where we have to bring up another topic called fan out. So BGA fan out style basically comes in two varieties. There is dog bone fan out, and it's because of the shape of these different pieces that you add on to each of these balls. And then there's via in pad. And via in pad happens once you get really close together. And so we'll see why in just a moment. So for dog bone fan out, basically the way this works is here you have your main pad, and this is where the actual soldering is going to happen on this pad in your footprint. Then what you'll have is you'll have a small amount of trace that comes off to another pad with a via. What I'm gonna do is, on my outer layer, I can route directly into the BGA. So you'll notice this is right at the edge of the component. I can take a trace and I can just route straight in. Same thing right here. And then here in this internal ball on the next row, as long as these things aren't spaced too close together, I can route another trace in, and then I can just go like that. Same thing down here. I could just do that. And so you can kind of see how this pattern repeats all the way around the edge of the component. I don't have to do it from the center line down. I could have the center, I could have this trace come in here and go this way and connect here. Whatever's gonna be easiest for you. One of the dangers here, and one of the reasons that we might have to use an alternative fan out style, is what happens when this pitch gets really fine. So let's say we're working with a really big BGA, right? And let's say this is 1 millimeter, right? Well, 1 millimeter is 40 mils. And so if I route a 10 mil trace in between these pads, if this is my pad size, this is my pad size, maybe I've got 5 mil, that's a little big, but maybe I've got 5 mil here, maybe I've got 5 mil here, right? And then if this is 10, that leaves 10 mils of clearance between each side of the trace. So as this pitch gets smaller, these clearances get smaller, and that forces you to use thinner traces to route into this BGA. And the reason you have to go to thinner traces, well, it's because obviously you want to make sure that you don't make these clearances too small. If these clearances are too small, won't be able to be fabricated reliably. And then there's a risk that obviously if it's not fabricated correctly or your manufacturing tolerances are too wide, you create an unintentional short here where you didn't mean for it to happen. So as we get to finer pitch, we'll have to look at a different style, and we'll get into that in a moment. So that's routing into the outer layer. Now, how do we get to this guy? Well, we have a via here. That means we have to have another signal layer on the inner surface. And so to get to this guy, we can have a trace on an inner layer that just comes in and goes straight over to this via. It's gonna come up through this via, and then it's gonna touch this ball. And again, you can kind of repeat this process all the way around the BGA. So that's really nice because it lets you go through and figure out exactly how many of these layers you're going to need in order to totally fan out your BGA. So you'll notice you can fit this entire outer section of balls on one layer. Because you see I can route in 2 traces to hit these first 2 columns worth of balls. And I can do the same thing down here, and I can get to these bottom 2 rows. Same thing along the top. So you can use this process to count up how many signal layers you need. Now you might need plane layers in between. Let's say you're dealing with controlled impedance traces. Like blue has to be controlled impedance, same thing with red. Well, then we would want a ground plane between them. Then we'd want a ground plane underneath blue. So this is a nice way to help you count up how many signal layers you need, and then interleave that with plane layers. In fact, one strategy that is sometimes used in high-speed PCBs or in PCBs that use these bigger BGAs is you can actually use the row count or the column count. Do this for the largest BGA. You can use that count to figure out the total number of layers that you're going to need in your PCB stack up. We'll probably do another video on that another time, but right now I want to focus on breakout, or I should say on fan out. So here we've got a via coming off like this. Here we can have a via coming off like this. This one comes off like this. And so ideally this is kind of located centrally between these 4 pads that make up the footprint. And you just repeat this pattern all the way around. You know, I've drawn this with traces coming in here, but this doesn't have to be a signal connection, right? This could actually be ground. Same thing here. This could actually be a ground connection, or it could be a power connection, or whatever. It just needs to connect somewhere to an internal layer once you get to the inside of the BGA. That's essentially how you do it, is this fan out style. What happens when we get to finer and finer pitch? Well, I mentioned that the traces that route in from the edges have to also get thinner. Now, if these are controlled impedance traces, as the trace gets thinner, the dielectric thickness gets thinner. And you have to do that in order to maintain a controlled impedance, because if you remember from earlier videos where we've talked about impedance of a trace, the impedance for a trace is some function of the trace width divided by the dielectric thickness. So essentially what that means is that I can keep my impedance of my trace constant by just adjusting this ratio. So as W gets thinner, H also has to get smaller. So this is one of those reasons that very fine pitch BGAs need to be used in HDI, or you have to use HDI layout and routing techniques in order to work with those high pin count components. It's not just because they have high pin count, you need to have higher layer count. Within that high layer count, you need to be routing those controlled impedance traces on very thin layers in order to hit your impedance goal. The other thing that happens when we get to thinner and thinner or smaller and smaller pitch values, you know, these balls get closer together, but eventually what happens is the pad around this trace starts to get very close to the annular ring around this via. And so eventually you start to violate your clearances. Now you can, overcome that a little bit by making this hole smaller and smaller, but eventually this will get less than, 6 mil, and you'll have to go to an alternative fabrication style, so you can't reliably do mechanical drilling anymore, and you'll go into microvias. So we kind of briefly mentioned microvias in another video, and we'll go into that a lot deeper in an upcoming video. And then eventually, once this gets really small, you won't be able to fit a via with a hole here anymore. And so what happens is you'll actually have via in pad. So you will have your ball, you'll have your pad, and then the via will be put into the pad. And then that's going to be filled with a conductive material and then plated over, so that way you can solder onto it. So that's what happens in the fabrication process and the design process to make sure that as this thing gets tighter and tighter and more compact, eventually the via is just going to sit right here in this pad. I mentioned earlier that we have some solder mask expansion going on here, and so how big does that actually need to be? You should look in your data sheets. Also, check that the recommendation in your data sheets and what your fabricator might recommend is actually in your footprint. So what I want to do now is I want to compare a couple of different BGA footprints. Essentially what we're going to do is we're going to look at when this solder mask expansion is needed and when it might not be needed. So what we're looking at now is just an example PCB layout that we sometimes use to show off. You can probably tell right here in the very central area of the screen, we've got a very large BGA, but actually if I just zoom out just a little bit, there's actually 3 BGAs on this board. There's one here on the right, there's this other one that I was referring to, and then there's a third BGA that's actually right here. And so this is what I was saying earlier with, sometimes they have some odd footprints. Now right here, this is, if you look here in the description, it is a DRAM component. So this is a DDR2 memory. Let's look at this, these different BGA components a little deeper. So if I go over here to my view configuration, actually let me turn off single layer mode. Here you can see which layers connect to the different pins on this PCB. And if you actually look around here, what you should notice is that there is a whole lot of ground that is connected to this PCB, okay? Or sorry, to this BGA. So as I zoom in, you can see all these different vias here in the layout. And all of these vias here that are shown on the screen, most of them are ground. Here we've got some voltage, here we've got some voltage over here in the lower right corner, but for the most part, they're all connected to ground. This is typical for a BGA that has to consume a lot of power and that needs to operate with very low noise. It's going to run with a lot of power and ground connections, sometimes at multiple levels. So we have an upcoming example, and that is actually going to show you how to segment out a power plane to do exactly this type of stuff where you need to connect multiple power levels to a single component or to different groups of components. If I look at the solder mask, you can actually see what the opening looks like. So let me just zoom in here to R16. So here, this purple region around the pad here, this is the solder mask opening around the pad where the BGA is actually going to solder. And then here off to the left, we have the ground connection. So if I just really quickly measure the thickness of that opening, I get 4 mils. It's a pretty small opening. So these vias are also not really that small, actually. So this is only 10 mil vias and then 20 mil pads around, so 5 mil annular ring around each via. They're not the smallest, but this is still a really big component, and it still has a lot of connections on it. So you can kind of see here as I zoom out that there's a lot of connections on this guy. This is just a really good example that shows what happens once you start to get your pitch much smaller. So just give you kind of a good example. So here, this is pretty good sized pitch. I mean, here in the X distance, it's 1.461 or 416 millimeters. But here, check this out. If I zoom out, I've rotated this 45 degrees. So that's not actually the pitch. The pitch is going to be diagonally. So let me measure this. So here you can see the pitch is actually 1 millimeter. This is a pretty big component. It's got decently sized pitch. And so in this example, you can fit a 10 mil via with a 20 mil pad or 5 mil annular ring in order to route into the inner layers. The track width is also pretty wide, so it's 15 mils. But you can see here, I've got plenty of space for all of this, even with the 4 mil wide solder mask opening. If you're working at 1 millimeter BGAs, this is totally acceptable and will be manufacturable. So you'll notice these are all ground connections. On some of the power connections as well, I've also used the thicker traces, so 15 mils. But look at these traces. Okay, 5.5 mils. So why are these ones so small? These ones are so small because these are carrying signal, or if we get over to here, these are carrying a trace that is carrying a signal. So this signal down here is actually going somewhere else, going over to a capacitor, and then that's going off and carrying the signal somewhere else to a different component. Here on this board, we've actually intentionally kept the via size at 10 mils. That's because we don't want to have to go to smaller vias, which will cost more during manufacturing. And when you're dealing with high via count like this, especially in this type of component, I mean, there's like thousands of vias on this board, not thousands, but there's many hundreds of vias, and I think it approaches 1,000 as a total count. Those costs add up, and they do add up to quite a bit. This is a 6-layer board too. So again, those all add up. Let's just take a look at top solder. So here, the top solder, you'll notice that it exactly matches the pad on this particular component. And so this was actually done based on the manufacturer recommendations. This is something where it doesn't hurt to just ask your fabricator, hey, we have this particular component, it uses this size pads. Here this size is, so it's 15.748 mils. So decently sized pads, but it doesn't hurt to just ask them, hey, we're using this particular component, it has these size pads. Do you recommend having a wider solder mask opening on these pads? Manufacturer's data sheet says this. Can we go wider or should we just leave it? They may tell you to just go with what's in the data sheet. Those are often vetted pretty thoroughly, but it doesn't hurt to ask. So on this other one that we looked at, same thing. This was done based on manufacturer recommendations. And part of the reason they put together those manufacturer recommendations is because the size of the actual ball on the bottom of the component, that's going to vary component to component. So even though they have similar pad size and they have the same pitch, they may have different size balls on the bottom. And because of that, you may actually need that solder mask opening in order to hold all of that solder in place during assembly. So hopefully that gives you some ideas to what actually happens on a real BGA. This is rotated 45 degrees. And so that's why these dog bone traces that are part of the fan out run vertically and horizontally, rather than at a 45-degree angle like you would expect. And so if you notice over here in this other one, they do all go 45-degree angle. So Altium Designer will apply this style for you automatically. There's a feature that will do it. There's an upcoming tutorial video coming up that will actually show you how to do this, and you can follow along with that in your own copy of Altium Designer to work with your own BGA components. So this is kind of the bare bones of BGAs, and I know it's a lot of stuff to absorb, especially if you're a new designer. Hit that subscribe button, hit that like button. You'll get to see more videos where we talk about this kind of stuff, and we'll have another video on microvias and some stuff on HDI routing to hopefully help you understand what all of this stuff is. Thanks for watching. Leave your comments and questions in the comment section. Check out some of the resources that we have in the description. And last but not least, definitely don't forget to call your fabricator.